Hello, today we're going to talk about time scales and cycles. How do we use time to our advantage? How important is time when we're talking about climate change? And how can we leverage cycles to be a solution? So when we left off, we were talking about carbon dioxide rising, and that was causing our temperature to rise. And so here we see some of those greenhouse gases. The red line's methane. The blue line's carbon dioxide, and then the black line represents temperature. And what we can start to see by this ice core data is that the red line kind of spikes up this way, and then the blue line kind of spikes up this way. And what we see is those both kind of go off the chart from their normal ranges. And that all happens in the most recent years. This one goes thousands of years before present, so this goes all the way back to 800,000 years before present, which is a really long time, right? But now we're seeing this huge spike. So when we're talking about time scales, it's really super important, especially when you're looking at a graph like that, because there's two kinds of times we're thinking about: geologic time scales and human time scales. So geologic time scales are over a long period of time, so we're talking hundreds, thousands of years, and it encompasses all of the 4.54 billion years of Earth's history. Human time scale, on the other hand, is centuries, decades, or less, so something relatively recent. So you look at a graph like this one on this slide, and what we see is that, Earth's temperature is changing and Earth's carbon dioxide is changing, and then we see this kind of hockey stick that sticks up right here. And so then in order to kind of unpack that, if we take just that dotted line area and we stretch it out, and what we start to see is that as we stretch that out, it still has that upward trend. It still has that almost a hockey stick shape to it. And that's important when we're starting to talk about timescales, because we can see the impact that the human beings are having. So here on this graph, the center line, the center black line, represents present day temperatures. And if we look back at past temperatures, so we're talking 485 million years ago, we start to see this red line. We have swung way down, we have swung up above present day temperatures before. But what you'll notice is when we have those spikes, we see these mass extinction events. And so what we're starting to see now is that upward swing, and scientists are noticing that we're having one of those extinction events. Another thing to think about when we're looking at graphs of global climate data is to pay attention to scales. So if we look, notice how the scale changes across the bottom of the graph. What we have to watch for is that can muddy your data. It can make things look more or less important dependent upon how they stretch things out. And so we have to be careful not to muddy our data. But one of the things that we notice is that carbon dioxide, when we look at carbon dioxide, we can correlate that with the birth of civilization. When humans start appearing, and then when we start using coal, you'll notice that little red blob of red right over there. That represents the Industrial Revolution. And we can see that carbon dioxide is increasing because of what humans are doing. So when we start to look at human timescale, there's this website here. This is another cute little image that starts at 20,000 years before Common Era. And so if you click on it, you'll notice you get some fun little pop-ups. I'll let you go through this on your own and look at that link on your own. It's kind of sarcastic, kind of funny, but also kind of fun. Another one that you have are temperature spirals. Here's another one. This is just from late Industrial Revolution till now. This is talking about global climate change. So it started at 1850 in the center there, and what we're seeing is as the years progressed, the temperature line keeps going outward and outward and outward. And you'll notice it's got some variation for months, as we would expect for seasons, but we can tell that it started there in the center and worked its way out. We can also correlate that to ice volume. This is 1979 to 2017. What I love about this graph is it shows that beautiful thermal inertia that we've talked about before. So instead of seeing your peak ice where it's farthest out, being in that November, December, January, February time, you'll notice it's swung around over here where we would consider springtime to be, because we had some thermal inertia keeps that ice there a little bit longer. And you'll notice that during the hottest months of the year, that June, July, August is not where the low ice amounts are. It's a little bit later in the fall. Again, thermal inertia. So that's important when we start talking about that geologic time scale. Our oceans are going to show that thermal inertia for about 100 years is the estimation. And so when we're talking about our coral reef example, it's going to take a human time scale of about 10 to 12 years for corals to recover. And just that 2-degree change causes corals to bleach because they either starve or they get infections, infestations, whatever. So human time scale, we can see impacts on things like corals or like habitats. Invasive species is an example we've talked about, but we also have to start thinking at the global climate scale. Now here's one when we start thinking about countries. Let's see. Oops. Gotta click it, but I gotta find my mouse. There we go. Okay, so this one starts in 1880. You'll notice USA's down here. White means no change, red means a lot of change, and then we have dark blue, which means cooler. And so what you start to notice are, just kind of compare countries. Notice how the USA doesn't seem to change much. And sometimes we'll see lots of blue pop up. That's that El Nino, La Nina cycle that's impacting our temperatures. And notice how the United States is kind of not one of those great big red countries. And some of those are big countries. And Russia we tend to think of as cold and farther north. And why is it all of a sudden warming so much? What we start to see is the warming happens more towards the poles, less towards the middles. And notice how we don't change that much. And if we don't change that much, we're still one of those big global climate forcers. One of the biggest is China. They're ranked right up there with us. If we don't see a lot of change, our human population, our country, we might not be ready to make change. But if we're one of the ones who are causing the problem, what's our social responsibility in that global community? And then how do we change it, right? So one thing that's important to learn about is the carbon cycle, because the carbon cycle relates directly to climate change, because this is exactly what we are influencing when we're talking about global climate change. So how exactly do we contribute to that carbon dioxide? So by industry, 38% of carbon dioxide comes from our electrical industry, 32% comes from the transportation industry, 15% comes from manufacture, whether it's making and buying stuff or getting rid of that stuff. 9% comes from household use, so whether that's your water, your heating, stuff like that. 6% is that other. Other meaning like what places we don't necessarily know about, like decomposition of, your backyard waste or other stuff that doesn't fall into those major categories. So we have been focused on the impacts of like the combustion of fossil fuels, but we tend to think of a cycle as a circle, but it's way more complicated than that. So when we're talking about greenhouse gas and climate change, we're talking about this carbon dioxide in the air. And the fossil fuels come directly from this decay, burial of old stuff, right? And part of that comes from what happens in the ocean. So diffusion and salt and keeping that stuff in the ocean is a big piece of that. So what exactly puts stuff into the ocean? Those are going to be also known as sources. You're going to hear us say sources. So volcanoes, formation of certain kinds of rocks, cellular respiration, not like breathing, but like anything that does convert sugar to energy, that's cellular respiration. So respiration at a cellular level. Decay of biomass, because those little Microbes also do cellular respiration, and then burning of fossil fuels. And 60% of that carbon dioxide stays in the atmosphere without any direct balance. We'll look at the balances here in just a second. And then out of the atmosphere, or sinks, is photosynthesis. Hopefully you remember little SpongeBob there. Weathering of another kind of rock, granite, and then burial of that biomass. Once it gets down in that deep sediment, it stays there unless we burn it as a fossil fuel. So that's one of the reasons that's super important. To take it that far down into the earth takes a long time, a geologic time scale, but to burn it as a fossil fuel is done in a human time scale. So that's the part that's pretty important. That's the piece that's not in balance. Dissolving it in seawater is a place that we might be able to leverage a solution because it's an active reservoir, meaning it's always working to store carbon dioxide that will keep that there for a long time, 10 to the 8th. So if you write that out, put 8 zeros behind that, and that's a really long time because what happens is that carbon dioxide forms carbonate in the ocean, and then the little sea creatures use that for their shells, and then it sinks down to the bottom and becomes sediment, which then gets trapped and so on. So the ocean can be a big place for us to keep that carbon. So if we start thinking about the time scale, how long does it take to absorb or release carbon? Things that are short, which take minutes, hours, or days, is photosynthesis, cellular respiration, fire, volcanoes, burning fossil fuels, dissolving seawater, and decay of biomass. So lots of the things of the carbon cycle fall on that short time scale. Only a few things fall on the long side. Sediments, so whether you're burying it on land or making sediments in the ocean, and the rock cycle. But then we also have to think about which ones are sources for carbon dioxide and which ones are sinks, because that's going to directly impact that carbon dioxide in our atmosphere. So take a second, pause the video here, and figure out which ones are sources, which ones are sinks, and which one might be both. There's one that's both. Alright, so now that you've restarted the video, hopefully you did practice, what you notice are sources are in red, sinks are in purple, and the one that's both is in yellow. And what we start to notice is, look where all that red is. That red's on that short, and our sinks are not necessarily in there, and I kind of combine some of the sinks in terms of that sediment piece. But when we look at our sinks, whoa, we've only got one that's short, we've got the other two are super long. And so now, if we're starting to talk about solutions, we have to figure out how to make these happen faster or more photosynthesis happen in order to leverage the carbon cycle. So if we actually look at quantities, we'll actually look at amounts. This image has amounts. So which one is the biggest storage spot? The ocean. You'll notice how much, what a huge quantity is stored in the ocean, whether it's at the surface or whether it's in the deep ocean. Our ocean is the biggest storage spot for carbon dioxide. If we look at photosynthesis and cellular respiration, though, one thing that's important to notice is who wins? If cellular respiration puts in 60 gigatons, 61.3 is actually used in photosynthesis. So photosynthesis should be drawing more carbon dioxide out of the atmosphere, but what we're still seeing is that atmospheric carbon dioxide is rising, so we still got to figure out why. So if we look at ocean exchange, again, what we see is more carbon dioxide should be going into the ocean than what is coming out. So again, but atmospheric carbon dioxide is on the rise. So why? What's happening? If we look over here at fossil fuels and cement, we see 6 gigatons per year, which when on the rest of these numbers seems like a pretty small number. But that's unbalanced. Notice how there's no other arrow that goes with it, unless you count this ocean uptake one. But even then, that's still 4-ish gigatons a year. That's not in balance. And this is coming from this recoverable fossil fuel storage spot. So that storage spot is 4,000, where soils, vegetation, and spoils is only about 2,000, sediments only about 150, and it doesn't even compare to the ocean, but that's still a pretty big storage spot. And what we're doing is we're taking all that carbon out of storage and we're putting it into the atmosphere. So what's the implications of that? Human impact is still small in comparison to the overall carbon storage. But the climate is still changing because humans are leveraging that carbon cycle, and we're taking that carbon out of storage and putting it into the air. Normally, natural sources and sinks are balanced, and we are unbalancing that. So carbon is rising, climate change is real, and climate change is due to human activity. So what's the implication? Do we stop there and say it's hopeless? No. We have to figure out how to leverage that carbon cycle in our favor. And there are ways to do that. So carbon capture and sequestration, that's catching the carbon and holding it in place. To sequester means to hold in place. Currently, that's really expensive, and places we can do that are in the oceans. We're going to look later at a short little mini lab about how to do that, but it's got a drawback of ocean acidification. It makes it more acid, so our little corals can't recover. If we use rocks, but that's on that long time scale, how do we make it a shorter time scale? Or trees and plants. There's a YouTube video I'll let you watch that's a Vsauce, I believe, a fun little video about where trees get their mass. And so trees and plants could be one of those ways that we leverage that carbon cycle. Another thing is to reduce what fossil fuels we burn. We're not going to run out of fossil fuels. We're too smart for that. We care too much about our energy to run out of fossil fuels. So we're smart. We're going to figure that part out. But what we can't do is figure out and just let that carbon keep accumulating in our atmosphere. So one of the things to think about are carbon neutral fuels. Things like biofuels, which are made out of trees and plants. If they're taking the carbon in and then we're putting it back into the atmosphere instead of using fossil fuels, the carbon in is balanced by the carbon out, and that becomes carbon neutral, and the natural processes can continue to take place. Another way is to use low or no carbon dioxide alternative fuels, so things like wind, solar, fuels that don't necessarily produce carbon dioxide. And then also changing how we use our electricity. If we avoid peak hours, we charge or use our appliances overnight, what happens is that puts less requirement for fuel to be burned, like coal here in Nebraska. And so that reduces our carbon footprint. And then reducing use. Natural light uses obviously less carbon dioxide, and that's why we keep the lights off in 305 so much. LED lights don't use very much, and then we start getting more with CFLs and a whole lot with incandescent bulbs. So there are solutions in place. We just have to be willing to use them. So hopefully carbon cycle makes a little bit more sense, and hopefully you're feeling better about leveraging solutions.